Hello everybody, today we are going to be going over collisions and the conservation of momentum theory. So if you haven't already, I highly recommend to watch the video on momentum and impulse before this because a lot of those concepts will be used in this video. So first, let's define the two kinds of collisions there are. So the first kind of collision is called an elastic collision. And the other one is called an inelastic collision. So let's define what elastic collision is first. An elastic collision is when two objects collide and then they bounce off each other or they remain separate. So an example would be two pool balls. You have two balls here, and let's say they hit each other. Afterwards, after they hit, they'll just bounce off each other and then they'd go separate directions. So that's what an elastic collision can be defined as. It's when the two objects that collided remain separate after the collision. So on the other side, an inelastic collision is when the two objects combine together and make something like one big object after the collision. So an example of this could be like a car crash. You can have one car here, another car here, and then let's say this car is moving slightly faster than this car. When they collide, they will both be moving together in the same direction. So to quickly go over, an elastic collision is when the two objects, after they collide, they remain separate. An inelastic is when, after the objects collide, they remain together and they're treated as one object. In both cases, the total momentum of the entire system is conserved, meaning that the total momentum before and the total momentum after the collision are the same. So in an elastic collision, you can take the momentums of both of the objects and then add them together, and then it will equal to the total momentum after. And the same thing for the inelastic collisions. The total momentum, so the momentum of this object and this one is equal to the momentum of this one. So another quick thing to go over is that an elastic collision, the total kinetic energy is conserved, and an inelastic collision, some of the kinetic energy is not conserved. Some of it gets transferred into heat, sound, or other stuff. So let's go over the formula for an elastic collision. So an elastic collision, like I said before, the total momentum is conserved. So you have, and if you remember the formula for momentum, it is the mass times the velocity. So for an elastic collision where you have two objects that remain separate, you take the mass of the first object and its initial velocity, so the velocity, add it to the mass of the second object and that's initial velocity. Sorry, initial there. And then it is equal to m1, m1 v1 final, so the mass and velocity of the first objects, but its final velocity, added to the mass of the second object and its final velocity. V2 final. So this is before the collision, and this is after the collision. And then for an inelastic formula, so when the two objects combine together, you get something that looks like this. So you have the mass of the first object and the velocity of the first object and its initial velocity, plus the mass of the second object and its initial velocity. And here it gets it looks a bit different because you get the two masses added together multiplied by the final velocity. So the two formulas are really similar, but there's slight differences. And again, this is before, and then this is after. So if you don't know what the symbols stand for, the M1 is just the equals the mass of the first object, object 1, and then v1 is the velocity of object 1, m2 mass of object 2, v2 is equal to the velocity of object 2. And then v1 final is equal to the final velocity of object 1. And then v2 final is equal to the final velocity of object 2. So the most important thing to keep in mind is that the momentum is conserved throughout the whole collision. So before and after and during. The momentum is always the same. So we can do a couple example questions right now. So the first one, we have two cars. And let's say they're driving on a highway. And let's say they are driving into each other. So it'll look something like this. Two cars are driving into each other. And let's say the first car has a mass of 1,250 kilograms and is moving at a speed of 20 meters a second. And then the second car, let's say, is 1,000 kilograms and is moving at a speed of 25 meters per second. So keep in mind the direction that the cars are moving, because that's an important thing to realize. Let's say the collision is perfectly inelastic, meaning that the two cars are combined together afterwards and they are treated as one object. I want you to determine the momentums of the car before. So determine momentum of each car before. And then I want you to determine the total momentum of the system. So total momentum before. And then after, I want you to calculate the speed and direction after the collision. So the speed and direction of the car is after the collision. So you can take a moment and pause the video here to do the question, and then I'll get started on the formula and how to do it. So first, we want to determine the momentum of each car before. And that is pretty simple. We know the formula is for momentum is mv. And then we could just simply take the numbers and then plug them in. So you want to be consistent as well with the direction. So if we treat the car going right, so this one here, as positive, then we have to treat this one as negative. So let's take the first one. We get, and remember to use brackets, 1250 kilograms times 20 meters per second. $25,000 kilograms times meters per second, because that's the unit we use for momentum. And you do the same thing with the other one. You get 1,000 kilograms. And this time, since it's going in the other direction, we make it a negative 25. Negative 25 meters per second. And then you simply just multiply them out. And you're left with it equals to negative 25,000. So the total momentum of the system before the collision, if you look up to our formulas, this is an inelastic. So the total one is just the mass of the first one times the velocity of the first one, plus the mass of the second one times the velocity of the second one. And since here we found out that they're actually equal, the total momentum is actually equal to 0 before. kg times meters per second. So you just add these two together to get the total momentum, and you get 25,000 plus negative 25,000, which equals to 0. So the total momentum equals 0. And then for the final question, we can find out using the second formula. So this formula here. Since we know what this number is right here, the momentum before, the mass 1 times velocity initial plus mass 2 times velocity initial for that one. You can just do the same calculations, always show your work. So we have the first mass, which was 1250 kg times the velocity, which was 20. And you go, and you add it to the second one, plus 1,000 kilograms times negative 25 meters per second. It was 25, right? Yeah, it was 25, good. And then as we know, that equals to 0, but that also is equal to the two masses, m1 plus m2, times the velocity final. So we know the first one is 0 and equals to 1250 plus 1,000 times velocity final. So you get 0 equals 2250 times velocity final. And then to find the final velocity, you would divide both sides by 2250. And 0 over 2250 is equal to 0. So the final velocity is equal to 0. And in this case, since the final velocity is equal to 0, there is no direction. And then that's how you calculate the final velocity. And now it's not always going to be 0. Let's say the numbers I just chose here made it lead to 0. If we change up the numbers a little bit, it'll be a different number, obviously. And you want to make sure to, whatever your final number is, if it's negative or positive, you want to make sure to write it in the right direction. So in this case, we wrote that the going to the right was positive. So if our final number was positive, we would want to say it was going this fast in the right direction. Or if it was negative, we would say it's going this fast in the negative direction, or the left direction. So the numbers I chose here just made it end up 0, but if we change them up a little bit, you'll get a different answer, and you'd have to compensate for that by writing the direction. So let's go to our next example, where we have 2 bowling balls. So 2 bowling balls weighing 5 kilograms each bounce off each other in opposite directions. So they go this way, and then they bounce off each other, and then they're going the other way. So let's say the first one is going at a speed of 5 meters per second, and the second one is going at a speed of 3 meters per second. And then we have to, the velocity of one of the balls after is 2 meters per second. So let's say this one is going at 2 meters per second after. I'll write that better. So I want you to calculate the total momentum of the system before they collide, and then I want you to calculate the final velocity of the other ball. So to do this, I'll just give you a moment to pause and then work on the problem yourself, and then I'll just get started. So this is an elastic collision since the two objects do not combine afterwards. So we can just use the formula right here. So what we do is simply take the momentum before. So we want to calculate the total momentum before the collision, which is simply m1 times velocity 1 times m2 v2 on all the initial velocities. So the velocity, since they both weigh the same, you can put in 5 kilograms times the first one, which is 5 meters per second. And remember, it's going to the right, so we're going to label it as positive. And the next one here, we want to add it to 5 kilograms, my bad. And then this one is going the other way, it's going left, so we're going to treat this as a negative, which is negative 3 meters per second. So once you do the calculations here, you get 5 times 5, you get 25 here, and you get negative 15 there, plus negative 15, and then you just add them together, and you get 10. So the total momentum before the collision here is 10 kilograms times meters per second. And as you know, because of the conservation of momentum, the total momentum before is going to be equal to the total momentum after the collision. So now what we can do is calculate the velocity of the other ball. Because we know the velocity of this ball here is equal to 2 meters per second, the final velocity. So you can just look at the formula, and you see we have the final velocity of one of them, and we just input that in, and we already have the masses, so we could just insert all the values that we know, and then solve using algebra for the final value. So we know that the first side equals 10, so we could just leave it as 10 here, because the first part is just equal to this, and then we just insert everything in the other side. So the mass one is 5, and then it's 5 kilograms, and then this is the one that we don't know, right? Yeah. So this is the first ball, so we don't know the speed of this ball, so we'll use it as vi. And then plus the velocity plus the mass, which is 5 again, or 5 kilograms. 5 kilograms, and we have the velocity of this one, which is 2, and it's going in the right direction, so it's positive, so 2 meters per second. And then you can simply just calculate it out. So 10 equals, that's 10 as well. So you get 5 kg times the initial plus 10. Then you could subtract 10 here, subtract 10 there. You get 0 equals 5 kilograms times the final velocity, so v1 final. You divide both sides by 5. You can see where this is going again. 5, and you get 0 over 5, which is equal to 0. So the final velocity of the other object is 0. Bf equals 0. That's actually quite funny. I didn't choose these. I chose these numbers randomly, so getting 0 for both answers is quite funny. But if it was a different number, you'd get a different number or a different answer. Yeah, it's not always going to be 0, guys. I apologize for that. But you can see here that since you could have found out it was 0 earlier just by knowing that it's 10 here, you have 10 at the first side, and you have 10 here, and then by algebra. You always want to keep in mind direction. So if the final velocity was negative, you'd say it was going in the left direction because we're using the right direction as positive here. And if it was a positive number, you'd say it was going to the right. So that just about does it for these kind of collisions, you're gonna run into a lot of problems like these, and you just want to organize all your information, and then you want to organize the information, keep it nice and neat. I know I'm not the most neatest person, but as long as you know what object is going away, it's really helpful to draw a little picture like I've been doing with like these circles, just so like you know, like you draw an arrow here indicating which way it's going, and then you want to know if it's inelastic or elastic, so you know how the end result of the collision looks like, if they combine or if they are remain separate. So you want to read the questions carefully. I'd say the most important thing here is to keep in mind the direction that the object is going, because you don't want to mess up and lose a few marks by writing negative when it should be positive or writing the wrong direction. So always keep that in mind. I think that wraps it up. In the next video, we're going to be going over more energy, so like work, power, energy, and the conservation of energy thing that I mentioned earlier would be talked about more. This is mainly about momentum and collisions. And you can also apply impulse questions to these. So if you watched the video before, I talked about impulse and how it's the change in momentum. So it can ask you for the change in momentum here. And that's just simply the formula that we used before, which was force times time, or the final momentum subtracted by the initial momentum. And with that, I'm just going to wrap the video up. Thank you guys for watching. I hope this has been helpful.